Welcome. This is an updated version of my video on what I'm calling the fundamental theorem of vector geometry. This theorem has several parts, and the reason it is so broad is because the proof, they all start from the same place proof-wise. All right. The first statement of this theorem is a statement on the connection between the scalar product of two vectors, which can be calculated by the product of their magnitudes multiplied by the cosine of the angle between the two vectors. All right? Hopefully not unfamiliar to you, all these different elements of this statement. The next statement is very similar, but it's a statement on the determinant between the two vectors. And you get something very similar. You actually get the product of the magnitudes, but then we do the sine of the angle. You know what? Maybe it's prettier without these. All right, that's the second statement. The third statement is a lot of statements in one proof. The third statement is that you can take the vector v and you can decompose it into two vectors that are parallel to w and w's canonical orthogonal vector. In this way, you can write v as v divided, v divided by w times w plus v divided by the covector. What I'm calling covector, there are some other things that are called covectors also, but in this context it's just the vector that's w rotated by 90 degrees. That's what I'm calling this hat vector. I'm calling covector. All right, so you can decompose w into these two orthogonal vectors. And what the hell does this vector division mean? Well, I'm calling it the scalar division or the scalar projection. So it has something to do with the projection, as you can tell, and it gives you a number, just like the scalar product gives you a number. All right? And the way you can actually write this is, you can write this beautiful little thing here as, you write this as the scalar product between v and w divided by the magnitude of w squared plus the determinant between v and w divided by the magnitude squared of the covector. Isn't that beautiful? Oh my god. And then you can put this all together and you get we can write this as the cosine and one of these will cancel, so you get the magnitude of v divided by the magnitude of w, cosine theta w plus the same thing, really, the magnitude of v over w sine of theta w. Wonderful. You could probably put this outside of the parentheses and make this even nicer. So it would just be the parentheses and cosine, and that's pretty wonderful. Maybe nicer. Whatever. You can play around with it. All right. So this is our statement. Statements, you might say. All right. And the reason I've collected these all in the same proof is because, again, they stem from the same fact. They stem from the fact that if we take two vectors, let's take a vector v here and vector w here, or let's call this v, let's call this w. All right. Oh, they look like they have the same length. Let's not do that. Let's make this one a little bit more. So what we can do here is we can actually scale these down so they become unit vectors, and everything will be so much nicer then, because then we're living inside the unit circle. So let's say you imagine there's a unit circle here, and we make this new vector W star and V star that only go out to the unit circle. So we're kind of ignoring this part that's out here. All right, we can always get that back by multiplying by the magnitude, but I want to live in here. Okay, now we can make this construct here. All right. Ooh, did I change them? Doesn't matter. No, it's good. And now we can use the fact that I can make this composition. I can make this composition in here pretty easily, because I can say, well, I can write W star as, well, I can write it as this part here. Well, what is this part? Well, this vector that goes to here, well, that's exactly the cosine of the angle multiplied by the vector V star. So this is cosine of theta V star plus sine of theta times V star covector. Just immediately from this drawing here. Isn't that wonderful? And this will be the jumping off point for all the other results. All right. Beautiful. So let's take the blue one, the first one with the scalar product. All right. So let's consider the scalar product between V and W. Well, V you can write as its magnitude times the V star, the unit vector. And we can write this W as, scalar product of the magnitude of W times V W star. All right. We can rearrange this so these scalar products, so the magnitudes just stand in front, and then we can rewrite this W star as this thing. So we get the magnitudes out front, and then we have V star, and then we take the scalar product with this thing, so the cosine of theta, V star, plus sine of theta V co star. All right? And here what happens, we use the fact that V star and its covector are orthogonal. So when I take the scalar product, this actually just cancels. All right? So I get this times the cosine of the theta, the angle, multiplied by the scalar product of V star with itself. But when I take a scalar product of a vector with itself, I get the magnitude squared. But V star was a unit vector. It's designed to be a unit vector. So these actually canceled. And that was the very first formula. Wasn't that beautiful? It wasn't even that hard. I really love this proof. All right. So the next one is, hopefully I'm missing something, but I use this one. The next one is completely analogous. We do something very similar. So we take a determinant, and again we do the same thing, but instead of taking the scalar product between V and W, we actually take the scalar product between V's covector and W. All right. Same exact argument, and we end up with the magnitude of V, the magnitude of W, and then we get V's covector star, and then again cosine of theta V star plus sine of theta V star orthogonal. The orthogonal vector. Maybe the orthogonal vector is even better, and there's no confusion. Anyway, Same exact argument. This cancels because these are still orthogonal, since there's a scalar product here. And we get this magnitude times the sine of theta times this magnitude of this squared. And it's still 1. So these also cancel. Isn't that fast? It's almost too fast. It's going to be an exam question. It just feels like it's too easy. We'll see. The last one about the projections. Oh, shoot. There's a fourth one I forgot. There's a statement on the determinant here. Actually, I don't have to. I can reuse one of these. I can actually put it up here. Okay. So the determinant is actually the area of the parallelogram that is generated by these two vectors. So if you have those two vectors as the two sides of the parallelogram, then this determinant is going to give the plus minus the area of that parallelogram. But I'm going to do that. I think I'm going to do it now. Let's do it now. Because let's calculate the area here. Okay, so let's go with the area. What is the area of the parallelogram? How do you calculate the area of a parallelogram? Okay, so let's reintroduce V. Let's take the whole of V. And that's going to become the base of our parallelogram, right? But I'm not going to extend W quite yet. I'm just going to take the small parallelogram that goes from here to the end of V, but has this height still inside the unit circle, okay? So I'm going to call this A star, okay? What is the area of A star? Of this parallelogram, this shortened parallelogram? Well, it's the base, which is the length of V, multiplied by the height. And the height here is exactly this, the projection here, which was, so it was the length of length of V times sine of theta. I'm pretty sure length. Technically it's the hat, but it's going to be the same thing. Yes, this is it. But again, the height here it's actually just the sine. You don't need this. The height here is simply defined as the sine of the angle. So you don't need that unit vector. I think that's what was confusing me. All right, beautiful. Okay, so how do I get the whole angle area? Sorry, how do I scale this up? Well, I simply how I get from this small parallelogram to the big parallelogram. I just have to scale up by this the scale factor, and the scale factor is exactly the length of W. That's how much smaller this parallelogram is compared to the other parallelogram. So the whole area is going to be the small parallelogram times the magnitude of W, which is then simply the formula for the determinant. Wasn't that amazing? It says plus minus. That's because I'm actually also allowing this height to be negative. So if this vector came down here, then this height would produce a negative sign, and you would get a negative height. So you have to you actually have to remove the sign if you want the absolute area. Wonderful. The last one is really similar. If I want to calculate V there, yes. Yeah. So I'm going to start with W star, just like we had up here. So I'm going to start with this, and what I'm going to do is I'm going to multiply it by W Yeah, I think I got it. So I'm going to multiply this by the magnitude of W. I'm going to do the same thing on the right hand side. So I get the magnitude of W cosine of theta. But then I'm going to do another thing. I'm going to actually expand this fraction with the length of V squared. So one of the V's goes up here in the numerator, but the other magnitude goes out here. So I divide by two magnitudes here, but I multiply by two magnitudes also, or the square. All right? So I multiply by the magnitude of W, which goes through the whole equation, and I expand this by the magnitude of V. All right? So hopefully you see that I've done nothing to this part. I only changed the expression. I've not changed the value. All right? So the same thing to the other guy. I get magnitude of V, magnitude of W, sine of theta over the magnitude of V squared with magnitude of V star hat. All right, and that's actually it. I had to think about it for long, and then the actual argument it took. Because what's in the numerator here, it's exactly the scalar product. I've done this with W instead of V. Maybe I should have changed it over here, but hopefully you can just flip all the V's and W's here and get the same thing. What's over here? Well, we have the determinant in the numerator and this square of the magnitude in the numerator. And what this is, the vector times its own magnitude, is just the vector itself. So that's exactly what it says here. Yes, if I want to change it to this expression, all I have to do is I have to realize that the definition, if I want to prove this last expression, I just have to cancel one of these. If I cancel this, then it's just the magnitude of one vector divided by the other times the cosine. That's what this says. And to get to this, you simply use the definition of the scalar division or the scalar projection. The definition of the scalar projection is simply the scalar product between the we can write it down here. So A scalar division by B is simply A's scalar product with B divided by their, I believe it's B magnitude squared. And that's exactly what this is here. So this is the scalar product. Then so this is actually just the definition of the scalar division, is that this expression here is the same as the scalar division. All right. The reason there's a determinant here instead is because we have the orthogonal vector. All right. I'm not going to edit this because it's a pain in the ass, and I feel like it's more helpful just to see that nobody's perfect. Then it's okay to make mistakes as long as you figure it out, even if you get a little bit of help. But yeah, it's slightly sparse. I didn't do every single detail, but if you have any questions about any of the steps or anything, you know what you can do. You can always leave a comment or question in the comments. All right. See you next time.